Okay, so our presentation is Why Not? An Introduction to Knot Theory and Whatnot.
All right, so our essential question is what is knot theory and how is it used in the world in modern day society?
Okay, so with a very simple definition, knot theory is a field of math that provides a series of tools and techniques to analyze knots, which we'll get into what even are knots in a little bit, but we can analyze them and their attributes with knot theory.
Oh, yeah, in reality, that's just a simple definition. We're going to try and get more specific as we go along. I think this is you. This is your slide.
Oh, okay. The very basics of this: a knot is a closed 3D curve, like a circle that's been laced with one part going through the other, um, and that can be in any way. And you're gonna the math of it is studying the ways that they're laced through each other.
All right, so there's two pretty major questions that we want to look into when discussing knot theory. Is this knot really a knot, or can it be untangled into something like the unknot that we see here in this picture? As well as are these two knots the same? Which meaning like can they both be continuously deformed into the other to make the same exact knot?
Okay, so we're gonna start with the math of it all. I'm gonna go through these bullet points, and then I'm gonna show you them on a whiteboard in just a second. But first, you think of a knot is instead of just a knot as a finite number of edges. That makes it a lot more simple to kind of understand mathematically. And with that, you can alter it in a lot of different ways. So with the elementary knot moves, the first one being division, where you divide a certain edge into two edges by just putting a point in the middle. You can also erase that point and get back to AB. There's addition. Um, if a point does not lie within a knot, you can um, remove a certain edge and connect that point to the knot. Which I'm gonna show you these in a little to make it more easy to understand. But then again, you can also move backwards, erase the new line, and go back to the old one. And if two knots are only altered by elementary knot moves, they are technically equal, but they're not orientationally equal, which means they're the same type of knot, but they just are orientated differently. So just to get started with this, we can see that we have an actual circular rounded knot here, and then we have multiple edges here. This is what we're going to be working with for this presentation. I'm going to just erase these really quick just so I can show you the first elementary knot move. So if we start right here, we can see that we have, bear with me, we have A, which is this point right at this corner, and B right here. And now the first move is simply just adding a point right here, point C. So now instead of just A and B, we have AC and CB. And then the second knot move, elementary move, is just going back to AB and removing that point C. Okay, and the next one is going to be the addition. So if we add a point out here that does not connect with A, I don't know why I removed A and B, then one thing we can do is erase. I don't know if it's going to let me erase without erasing the whole thing, but imagine
The
AB
line,
is
yeah, the line connecting
removed,
A B will disappear completely in this scenario.
but we can always go from A to this point C and from C back to B. And then we can always go back to just AB. Those are the elementary knot moves. They're going to change the way that the knot looks, but they're not going to actually change what type of knot it is. Because the way it's laced through itself, its crossings are still in the same way, and there's the same number of them. So, to continue on with this math, there are a thing in knot theory called links, which are exactly what they sound like. They're a set of knots that are linked together, a finite ordered collection of knots. If two links L and L prime they are equal if they have the same number of knots, and you can change each of the knots in L into L prime just by using the elementary knot move. So they have the same type of knots, but they can be orientationally different. So decomposition is when you break one knot into two, which I'll show you in a little bit, and I'll show you trivial knots, which is when you decompose one knot and one part is still equal to the original knot. Composition is when you bring two knots together, and that's a lot more complicated mathematically, and I'm going to go about showing you why in just a sec. So starting off with links, we're just going to use a couple of unknots to make it go by pretty quickly. An unknot is just a circle, basically. So if I have this, and this can be link L. Or, yeah. And I'm going to make a slightly different looking one, but it's going to be linked in the same way and with the same. So yeah, this is just a knot. These are all unknots. This is L prime, and technically these are actually equal because just by using elementary knot moves, these three knots can just end up looking like these three circles. So we're just gonna go through that. That was the basics of links, and now we can go with decomposition. So if I draw a star really quickly.
In reality, like most knots aren't as sharp as the stars look, but it does make it easier for us to understand the different sorts of moves that we can do.
So I added this for a reason here. So if we're going to do decomposition, so which will be kind of hard to draw with like the eraser on this application, but we would cut it here. I'll just try to go like this, and then link it kind of like this. So ignore these two lines here, and then we're left with two different knots. We'll just call this A and B. And an unknot is what we have, or no, not an unknot. We have a trivial knot. So this decomposition was technically trivial because since there's no lacing or interlooping in this knot that we cut off, A is still equal to the knot that we had before. And now we can do composition, which is basically where we just go from this back to this. And the reason this is more complicated is because if we are sliced here, we have to indicate where this knot, first of all, splits up to connect to here. We have to define mathematically where each knot will link up back to each other. Cutting them off is a little bit easier, but when you're joining two knots together, you have to be very precise about where you're doing it on each of them.
All right, so knots that are fundamentally different are called invariants. Typically, it has to do with the number of crossings within a knot. As you can see here, an unknot obviously has zero crossings, therefore it has no invariants. And invariants are really created when the orientation of the crossings are very different. As you can see in this diagram here, with the 5 knots crossing, you have one that looks like a star shape, and then you have another one which looks fundamentally different than the other one. And this is pretty much consistent with all like number of crossings that you can have in a knot. Typically, there are more invariants when you have more crossings. As you can see here, there's I believe 7 knot invariants for seven crossings, and this is just mainly because you have like more like room to work, if you know what I mean. But knot invariants are very important to knot theory and understanding if two knots are actually the same or if they're really different. Okay, so tricolorability is a very important tool that mathematicians often use to define certain knots. There are 3 main rules of tricolorability. There's really only one that really matters. The first one is each strand of the knot can be colored differently. As you can see here, each strand of the knot has a different color that correlates with it. At least 2 colors must be used. Typically, it's 3 because that's why it's called tricolorability. But in reality, the rule is that only 2 must be used. And the third rule, which is what I found to be the most important rule, is that at each crossing, the three incident strands are either all the same color or all different colors. As you can see here in this top left crossing, you have a green, a blue, and a red. In the top right crossing, you have a blue, red, and green. And in the bottom one, you have a blue, green, and red. As you can see, all the crossings have each of those three colors in them, and that's what makes it tricolorable. Tricolorability is vital to helping people understand how the knots are formed and how they move and how they can like be composed, like decompose, and it's very important.
Okay, so wait, is this your slide or is this
This
mine?
is you. This is you.
Okay, so to summarize, there are four main elementary moves you can use with knots and see if they're equal. Um, all knots have crossings that produce some sort of polynomial expression, and that polynomial expression is can be changed with the elementary moves. But when you end up simplifying that expression, you're left with two equal knots that are orientationally equal um, and fundamentally equal. So knot theory also revolves around the manipulation of a knot to produce the same polynomial expression, and only when the two knots have the same polynomial expression, simplified polynomial expression, can they be considered equal. If the two knots do not have the same polynomial expression, they're considered knot invariants, and tricolorability helps us understand the characteristics of these knots. And there's obviously a lot more to this theory, but this is the basics. If we were going to do the whole thing, it would take hours.
Yeah. All
So,
right.
what's the big idea?
How is knot theory used in everyday life? This is part of our central question, and we really want to look into this as much as we can. So, the main thing that we found for knot theory being used in modern day life is with DNA. Knot theory is often used to model DNA because DNA is a long polymer change and it tends to form these knots. And with knot theory, these scientists can model DNA in any shape or form. Furthermore, it's very important to understanding topoisomerases. I believe I'm saying that right, but those are a type of enzyme that causes like the supercoiling of DNA, which means it's like really like coiled up. And then in total, like knot theory is often used to test different enzymes' impact on the knotting and coiling of DNA. So it's been very prevalent in the modern like science world, if you know what I mean.
Okay, so next is topology, and this is a area of mathematics that studies how spaces are organized and how they're structured in terms of position. So topology, in more simple words, I've thought about it as like just the study of the way things are in life, or like in the world, in a
Yeah,
space,
I think that's good.
how something's orientated, how you can represent it with numbers. And that was crucial to creating knot theory, but there's also knot theory has affected topology as well in the inverse. So it has been crucial to the development of major topological theories such as Chern-Simons theory, which is a very complicated quantum physics theory. Um, but basically, this is used to kind of understand physical things in a mathematical way.
Yeah,
And because quantum physics is still a kind of still a field we're learning a lot about, we could probably see knot theory ending up being used to help us better understand that field in the future.
yeah, I would definitely argue that topology in general, we did not understand it as well as we understood like how knot theory was used in DNA, but we did find that it was very important. So moving on, we have network topology. So network topology is like topology, but obviously in a network in like a computer like atmosphere kind of. And network topology is very important and key to determining a network's performance because it's really the way that the network is arranged, including the physical or logical description of how links and nodes are set up to relate to each other. And we are able to use knot theory to set up these links and nodes in order to produce the most functioning network possible. As you can see here in this bottom right diagram, we have all different like setups to network topology that produce different functionalities, if you will. And with knot theory, we can really create these different types of network topology. All right. So, in conclusion, knot theory uses 4 elementary moves in order to determine whether two knots are the same. Knot theory has a prominent place in the world today that we have found, especially in DNA modeling, topology, and network topology. And we do believe that it will have more uses as scientific advancements increase. But this is what we were able to find now, and this is how we are answering our essential question today.
So that was the end.
Here, show the works cited.
Those are our works cited.
All right.
All right, nice.
Thank you.